In this video, we are going to continue in section 2.2, and we are going to be looking at how we solve for the zeros of a polynomial function. When analyzing a polynomial function, we can determine two things pretty quickly. The first is how many real zeros the polynomial will have, and the second is how many turning points it has. And we could say that turning points are very important points, or you can call them VIP points. But turning points are basically just where the function is turning. So when the function changes from increasing to decreasing or decreasing to increasing, anywhere that you see a maximum or a minimum point, that's usually where the function is going to be changing and that there's going to exist a turning point. So let's look at a typical cubic function. So we could have something that looks like this. Okay, and this right here would have a polynomial function with the highest degree of 3. And we want to look at how many turning points it has. So we see in this function that it is decreasing, decreasing, decreasing until it gets to here, and then it begins to increase, and then when it gets to here, it continues to decrease again. So we would say that this function has two turning points, here and here. Okay, so this is a typical cubic function. Now, a typical quartic function might have a graph that looks like this. So now we can count the number of turning points again as where there's maximums or minimums. So we have a turning point here, a turning point here, and a turning point here. So we would say that the typical quartic function has 3 turning points. The typical cubic has 2. All right, now we can begin to develop a formula for determining the number of turning points, and we can say that for an n-degree polynomial, so an n-degree meaning that this would be a 3rd-degree polynomial, this would be a 4th-degree polynomial, this would be an n-degree polynomial. So we say that an n-degree polynomial has n minus 1 turning points at most. Let's go ahead and look at a couple of examples of polynomial functions. So you would be given a function, something that looks like this, an f of x function, and you would be told to state the number of possible zeros and the turning points for each function, and then also determine the real zeros by factoring. So the first thing we want to do is state the number of possible zeros. And because it is a cubic function, we know that there's going to be a possibility of 3 real zeros. So that's just the possibility. That doesn't guarantee that we're going to have 3 real zeros. The second thing we want to determine is the number of turning points. So if you remember, the turning points are going to be n minus 1. So our n in this case is 3. So we have a maximum number of 2 turning points because n minus 1, 3 minus 1 is 2. So we have 2 turning points as our maximum. Now we want to determine all the real zeros by factoring. So here we notice that there's an x that is common to all 3 of these terms. So we can go ahead and pull that x out. And we're left with x squared minus 6x minus 27 equals 0 because we want to find the 0, so we're going to set our y equal to 0. And then when we continue to factor that, we are going to see that this x stays out here. We want to look for 2 factors that multiply together to give us negative 27 and that add to give us negative 6. So we have x minus 9 and x plus 3 as our 2 factors. So simplifying, we can't forget about this x here. So our 3 zeros are going to be x equals 0, x equals 9, and x equals negative 3. So let's look at another example and factor and determine the zeros for this polynomial. So the first thing we need to do is think about what zeros we could possibly have. So how many possibilities of zeros do we have? And since this is a quartic function, we have 4 possible zeros. The next thing we want to look at is how many turning points do we have? So we have n minus 1 and our degree of this polynomial is 4, so we have 3 turning points at most. So remember, it doesn't necessarily have to be turning 3 different times, but we just know that this is the most it can be. Okay, now let's think about how we would factor this. Now this isn't normally an equation you would factor, but don't let this 4 and this 2, the square term right here in the middle, scare you, because it is really just a quadratic, but instead of using x and x, you're going to be using x squared and x squared. So let's continue factoring down here. So we have our parentheses here that we want to set equal to 0. And instead of x and x, again, we have x squared, and we can verify this by FOILing and doing the first term right here. So x squared times x squared is x to the 4th, which is indeed what we have here, so we know that we're on the right track. Now we want to determine what factors of 4, negative 4, will give us a negative 3 when we add them together. So that is going to be x squared minus 4 times x squared plus 1 is equal to 0. Now we just set these individual factors equal to 0 and solve for x. So this becomes x squared equals 4, because I want to add to both sides, and this becomes x squared equals negative 1. All right, now we can continue by taking the square root of both sides. So when I do that, take the square root, I get x equals positive or negative 2. Remember that we have to include that positive or negative. But here, when I take the square root, I can't take the square root of negative 1. So I actually don't have any more zeros here because this is not going to be a real solution. Okay, we could say that it's x equals plus or minus I, but this never shows up on our graph, so we don't even have to include it. Okay, so we know that the only zeros we have are at x equals positive and negative 2. All right, now let's look at the graph of this function. So I already have it pulled up on Desmos here, but let's look at what happens. So here I have my function x squared minus 3x squared minus 4, and I calculated my zeros to be plus or minus 2. And indeed, I see that right here in my graph that this value right here is negative 2, 0. This value right here is 2, 0. So those are the only places that cross my x-axis, so I can verify and conclude that those are my real zeros. Another interesting thing we can look at is the number of turning points. So like we said at the very beginning, we can have n minus 1 or 4 minus 1, a max of 3 turning points. So let's go ahead and label where those are. So we have a turning point here, we have a turning point here, and we have a turning point here. So we have verified that there are a maximum of 3 turning points, and we can see that in our graph. So let's look at one more example of how we can factor polynomials and then translate that information to a graph. So again, here we notice that because this is a polynomial to the 5th power, there's a possibility of 5 zeros. So we have a possibility of 5 real zeros. Okay, remember, we don't necessarily have to have all 5 real zeros. It could be a mixture of real and imaginary. And because our function is to the 5th power, we know that we're going to have 5 minus 1 or 4 turning points at most. So this is just kind of giving us the general shape of the graph. All right, now we're ready to factor. So what we do, we want to set it equal to 0, and we notice that the function has x cubed that is common to all 3 terms. So let's go ahead and pull x cubed out. So when we do, we have 3x squared minus 18x plus 27. All right, so we're going to continue working through this, and we can do this 2 ways. We can either factor by grouping, or we could go straight to the quadratic formula. But here I notice that, yes, I factored out an x cubed, but I could also have factored out a 3 term because 3 is common to all of those terms. So let's go ahead and do that. So 3x cubed now becomes x squared minus 6x plus 9. So now this is a lot easier to factor, so we can continue 3x squared, open up our parentheses, and we want to ask ourselves what factors of 9 will give us minus 6, and that's going to be minus 3 minus 3. Okay, so we're starting to see something a little bit interesting here with this function, because when we set the equal to 0 and solve, we get x equals 0 from this term, but this is going to have a multiplicity of 3, meaning that this 0 occurs 3 times. And the other two, this x minus 3, this is going to be x equals 3, and this has a multiplicity of 2, meaning that this root, x equals 3, occurs 2 times on our graph. And when we graph this, we can see that at 0, because it has an odd multiplicity, at 0, it is going to cross the x-axis. But at 3, because we have a multiplicity of 2, which is even, it is going to touch. So we can verify that by looking at our graph. Looking at the graph, this is only a partial version of it, but I really only care about what's happening at the zeros. So I see that I do have a 0 right here at x equals 0, and I also have one at this point, which is x equals 3. But notice the behavior. So at 0, my function is increasing, and then it's crossing here at 0 and continuing. At 3, it is decreasing. When it gets to 3, instead of crossing at 3, it goes back up and begins to increase. So I can see that when my multiplicity is odd, meaning if I have x to the cubed equals 0 and I said x equals 0, I would see that my 0 is repeating 3 different times. So I had odd multiplicity. My graph at that point is going to cross. If I have even multiplicity, so if I had x squared equals 0 and wanted to solve for x, I would get x equals 0 with a multiplicity of 2, meaning it's occurring 2 times because of this squared right here. Even multiplicity, meaning it's going to touch at the axis. So at 0, remember we said because it was a multiplicity of 3, it's going to cross, and we can see that in our function here. And then at 3, because it has a multiplicity of 2, which is even, it's going to touch, and we can verify that by looking at this graph here. Just a quick recap, we can determine the number of possible zeros by looking at the highest degree. So if we had an x to the 4th function with a bunch of other terms, we would say that there are 4 possible zeros. And then turning points comes from taking this number and subtracting 1. So we have at most 3 turning points. Now, finding zeros of the polynomial requires that we set the polynomial equal to 0 and then factor. If we get zeros that have an even multiplicity, so meaning they occur 2, 4, 6, any number of even times, our graph is going to touch at that value. If we have a 0 with an odd multiplicity, meaning it occurs 1, 3, 5, or any number of odd times, our graph is going to cross. So this is just a couple ways that we can begin to analyze our function.